So it's a pleasure for us to have Professor Ping Zhang with us from the State Key Lab of Math Science and the Academy of Science, Beijing in China. He has been many times, I think, visiting. I told him there would not be too many people because of bridges, but in fact, many people. So it is excellent. And we're happy to have him speak about analyticity radius of Navier-Stokes equations in 3D, please.
Thank you very much.
The floor is yours.
So I would like to thank Professor Katerina Schwartz for inviting us to visit Zhang's laboratory. I also would like to thank the organizer of this colloquium, by Professor Kong, Professor Hong, and Professor Liu Han. It's really my great pleasure and honor to be back to Jacques-Louis, where I learned a lot from many mathematicians here, like Zhang, Professor Hong, and many others. In fact, the title, the reference, I'm going to speak today is I learned many years ago from Zhang. The title is like refined analytic radius of 3D Navier-Stokes equation. So let me write down this equation of 3D Navier-Stokes equation of V dot where V minus new Laplacian of U V plus where of P equals 0, and we assume this divergence precondition of the velocity field. So we also define the Laplace projection operator equals identity map plus gradient composite minus Laplacian inverse of divergence, which is called Laplace projection operator for divergence free vector field. So if we apply this Laplace projection operator on this equation, we would obtain equation of this type, called 3D Navier-Stokes equation, or the more general version of Navier-Stokes equation. Like particle T of U minus Laplacian U equals QUU for Tx in R plus times R3. Here, this U equals U1, U2, and U3. Denotes the velocity of the fluid. Q equals Q1 to Q3. And this QJMKL is Fourier multiplier of degree 0. And this QJUV equals the summation KJL from 1 to 3, QKLJMD partial M UK VL. So for instance, if you apply this Laplace projection operator to the classical 3D Navier-Stokes equation, you will reach equation of this generalized Navier-Stokes equation. So conventional wisdom, we know strong solutions to the spatial system like Kuramoto, Siwa-Shansky equation, SQG, small U Chomsky equation, Navier-Stokes equations. For this spatial system, strong solutions are in fact analytic in space and time variable as long as the time greater than 0. So the questions like optimal analytic radius of this solution. Physical implication of this problem is closely related to Kolmogorov type length scale in turbulence. So analytic radius leads to a low bound for Kolmogorov dissipation scale. For example, like a Kolmogorov open curve hypothesis. As the viscosity nu tends to 0, this energy band for this J, absolute value J, around K, less than 1/2, should be around K to the minus 3. As long as for K less than K star. And this should decay like K to the minus N for K greater than K star. So suppose we have this free coefficient of this u is like exponential to the minus alpha 0 nu absolute value of j, which means this function, the analytical radius of this function like alpha 0 nu. Then we have this k over logarithm of k should be greater than or equal to 1 of alpha 0 nu, which implies this energy band should be of k to the minus n. So if we ignoring this logarithm, this almost implies 1 of K star should be greater than or equal to this analytical radius. So a fundamental length scale for balancing the viscosity effects and the nonlinear inertial effects. And practically, this also yields like it should be scaling invariant and a scaling transformation like u to u lambda tx, which equals lambda u lambda squared of t lambda of x. It's easy to check if this utx is a solution to 3D Navier-Stokes equation with initial data u0. You'll find that this u lambda is again a solution to 3D Navier-Stokes equation, but with initial data lambda u0 lambda of x. We call all such spaces as critical spaces if the norms of which are scaling invariant and this scaling transformation. All the following spaces are critical spaces for 3D Navier-Stokes equations in the above sense. So what about critical well-postedness for this 3D Navier-Stokes equation? The first result is due to Fujita and Kato in 1964, where they proved, given each data in h dot 1/2, they can prove the local well-postedness of 3D Navier-Stokes equation. And for small data, compared with the viscosity, they can even prove the global well-postedness. It's easy to check h dot 1/2 can be continuously embedded to L3 and to this subspace B dot -1 plus 3 over P, PQ, and this subspace can be continuously embedded to BMO -1 for P greater than 3, less than infinity, and Q greater than 3 and less than infinity. In fact, Canonier Planchon proved, given each data in this subspace B dot -1 plus 3 over P, P infinity, large data, local well-postedness, small data, global well-postedness. The endpoint result in this problem is due to Koch and Tataru in 2001. They can prove the global well-postedness of 3D Navier-Stokes equation with small data in BMO -1. And in fact, one cannot prove even local well-postedness of 3D Navier-Stokes equation with niche data in B dot -1 infinity infinity. This result is due to Borgenda Pavlovich and also another result by Pierre-Hume. And even Pierre-Hume, Pavlovich, and Saflani can prove the solution of Cauchy-Tataru solution is in fact analytic as long as time t greater than or equal 0. So prior us on analyticity mathematically, it was proved by Matsuda in 1968. Like for 2D Navier-Stokes equation in a bounded domain with dirational boundary condition, they can prove the solution is in fact analytic as long as time t greater than 0. And Fouillage and Tman in 1989, they introduced called a Jerry norm. They introduced the Jerry norm and used energy method to prove the analytic radius of this solution is like over square root of t should be has a lower bound of positive constant sigma for some sigma greater than 0. So here, this Jerry norm means e to the exponential cosine t minus Laplacian square root at on u0 belongs to some subject space. And Gruch Kukovica 98 proved similar results with niche data in LP for P greater than D, and they can also proved the analytical radius over square root of T should have a positive lower bound. Eventually, Lamarier, he will say, proved in 2000, like for Fujita Katu solution with niche data U0 in H.1/2. Then he can prove there exists a time depends on U0 such that this integral of absolute value of cosine multiply supremum for t less than or equal to capital T e to the exponential square root of T of and times absolute value of cosine multiplied by Fourier transform of u t cosine square d cosine should be integrable. And if we also integral with respect to time, we gain one more derivative in space. So this result in particular implies the analytical radius of this solution ut over square root of t should be greater than or equals to 1. And according to the heat kernel, this appears to be optimal. So let's go back to the classical Navier-Stokes equation, which reads like partial t of u equals Laplacian of u minus Lagrange projection, great divergence over the on u tensor with u. So here, why we only study like e to the exponential minus t Laplacian square root act on u in some subwave space instead of e to the minus t Laplacian u act on u with some norm. So in fact, we have the following explicit example. So consider the space dimension equals 6 and u is non-negative, is positive. In this situation, this heat equation partial t of u equals Laplacian u plus the modulus of u times u, which equals Laplacian of u plus u squared. And for this equation, there is a called Orban-Tarenti bubble, explicit solution, ux equals 24 to the Japanese bracket of x to the minus 4. For this particular situation, it's easy to check its Fourier transform have optimal like exponential decay. So a surprising logarithm improvement due to Herbst and a skip state in 2011. In fact, they can prove given each data U0 in H gamma for gamma between 1/2 to 3/2. They can prove the 3D Navier-Stokes equation with initial data U0 has a unique local solution U on 0 to capital T. And they can prove for any epsilon between 0 to 2 gamma minus 1, there exists a time T0, which depends on epsilon gamma, H gamma norm of U0 belongs to 0 to T, and a constant C depending on epsilon gamma and H gamma norm of U0, such that this exponential Fourier multiplier with e to the exponential square root of 2 gamma minus 1 minus epsilon composite with square root of t times absolute value of logarithm of t composite with this absolute value of d act on this UTH gamma norm is controlled for all t between 0 to T0. Because the above estimate works for any epsilon greater than 0. So in particular, the above result shows this analytical radius of the UT over square root of t times absolute value logarithm of t as t tends to 0's lower limit should be greater than or equals to square root 2 gamma minus 1. So in the critical case, when gamma equals 1/2, do we expect this lower limit of analytical radius of this ut over square root of t equals plus infinity? And the other question is like the optimality for this lower bound for gamma between 1/2 and 3/2. And it seems 3/2 gamma equals 3/2 is a barrier because of the product law and the others. So in order to study this problem, joint work with Yuan Schumann, Isabella Gallagher, in 2000, we studied the following semi-linear parabolic equation. Partial T of U minus Laplacian U equals PU for Tx in R plus times Rd with niche data U0. So here this U equals Uj for J between 1 to N. This Pj of U equals the summation for L in the multi-index L of N with this length equals K. And this Fourier multiplier AJLD act on this product J from 1 to N Uj Lj. So here this AJLD is a homogeneous Fourier multiplier of degree beta between 0 to 2. And here the order of the nonlinearity is like K greater than or equals to 2. And the scaling for this problem is like lambda for alpha u lambda squared of T lambda x for alpha equals to minus beta over K minus 1. And for Navier-Stokes equation, which corresponds to beta equals 1, K equals 2, and for cubic heat, which corresponds to beta equals 0 and K equals 3. For this problem, it's easy to prove for any alpha between 1 over K to D over K, we define this as critical equals D over 2 minus alpha. Then we can have this classical local well-postedness of this problem. So in fact, we can prove the solution is analytic as long as time t greater than 0. We can prove if this delta is positive in the classical well-postedness theorem, then we can prove the analytical radius of the solution over square root of t times square root of minus logarithm of t times u0 h critical plus delta norm of u0 to the power 2 over delta should have a lower bound square root of 2 delta. And for delta equals 0, we can also have the following explicit bound. So this in particular proves as time goes to 0, this radius of this radius, analytical radius of solution over square root of t equals plus infinity. In fact, this part A echoes the Herbert's skip state for delta equals gamma minus 1/2. And part B quantifies analytical radius for the critical case h dot 1/2, h 1/2 for the classical 3D Navier-Stokes system. In fact, we can prove more. We can prove any global solution of 3D Navier-Stokes equation which belongs to C0 to infinity h 1/2 R3. This global solution should satisfy this analytical radius of this solution U over square root of t as time tends to infinity, the limit equals plus infinity. So for 3D Navier-Stokes equation, the reason why we can have a result like this is due to a result due to Gallagher, Iftimi, and Panchon that proved any global solution of 3D Navier-Stokes equation of Fujita-Kato solution should satisfy this limit as t tends to infinity, this h 1/2 norm of ut equals 0. That's the reason we can prove this global result. So this result does not contradict with open talented example which we present earlier. A sample of LP and a Besov type result for estimating this analytical radius of UT is available. Like for instance, for LP, for P between 3 to infinity. Lamahier, he said, proved in 2000, like this analytical solution, the analytic, as long as t greater than 0, and its analytical radius over square root of t should have a positive bound. And the same bound was generalized by Pibb. This was, and Professor talked about here, in class 2012 with niche data in B-1 plus 3 over PPQ for P between 1 to plus infinity. So an improved bound for data in LP. First, I proved with my student reading who, like a given each data use 0 in LP for P between 3 to 18 over 5. Then we can prove the system has a unique local solution. And moreover, we can prove this e to the square root 2 to the 1 minus epsilon over gamma composite with square root of t logarithm t absolute value composite with minus Laplacian act on this Vt with this surplus norm h dot 5 over 2 minus 6 over p should be finite for any t between 0 to t1. So this in particular, this result tells you this analytical radius of Vt over square root of t times absolute value logarithm of t should have the lower bound, like a square root of 2 times 1 minus 3 over p. So here, this v is not a typo. V equals u minus et Laplacian act on this u0. We can prove, in fact, for this v equals u minus ul. Satisfying equation like this, v equals b bilinear bvv plus bulv plus bvul plus bulul. We can prove for u0 in LP, for p between 3 to 18 over 5, the nonlinear parts, v should belong to like L, the weighted Schumann type space, L infinity delta t h dot 2 over 5 minus 6 over p, and in the space L1 delta t h dot 9 over 2 minus 6 over p. So with this regularity, this makes it possible to adapt this Hilbert skip state L2 framework to improve this analytic radius lower bound. So there is no reason for p between 3 to 18 over 5. For more general, in general, I proved in 2003 that given each data u0 in LP. For p between 3 to 6, here this lambda cosine equals summation j from 1 to 3, the absolute value of cosine j, like a small A1 norm of cosine. So now let U be the unique local solution of 3D Navier-Stokes system. We can prove there exists a small time T2 and a C2 such that there's a Fourier multiplier e to the exponential 2 times 1 minus epsilon over 3 gamma times 1 plus epsilon composite with square root of t logarithm of t absolute value composite with lambda d with t in this Besshoff norm should be less than or equals to C2 t to the minus 1 over gamma for any t between 0 to T2. So this in particular tells you as time goes to t plus 0 plus, this analytical radius of v of t over square root of t logarithm of t should have a lower bound like square root 2 over 3 gamma. So this covers a wider range of p than our previous paper. And furthermore, we does not rely on this L2 theory. But here, the disadvantage is that we have a big loss of analytic radius. So to prove this, it's crucial to use the Fourier multiplier ERT lambda d, which was first used by Lamarrière, Hissot in the paper of 2000. And we can also prove with same idea with niche data in the subcritical space U0 in B dot S PQR3 with P between 1 to infinity, Q between 1 to infinity, and S between -1 plus 3 over P to 3 over P. we can prove this solution as an analytic radius over square root of t logarithm of t. The lower limit has this lower bound like a square root of 2/3 times 1 plus s minus 3 over p. So note again, there is a big loss of this analytical radius compared to the case when p equals 2. So the status quo before 2024, the working space like H gamma, for gamma between 1/2 to 3/2, the lower bound is like analytical radius ut over square root of t logarithm of t, and the lower bound is like a square root of 2 gamma minus 1. And in the critical case, H1/2, we have this lower bound of analytical radius of ut over square root of t equals plus infinity. And for LP, for p between 3 to infinity, it was proved by Lamahia-Hissou, like analytic radius of ut over square root of t should have a positive lower bound. And for base of space, in the critical base of space, b dot minus 1 plus 3 over p pq, for pq between 1 to infinity, for small data, this was proved by Professor Tadmo and his collaborator. We have this analytical radius ut over square root of t has a positive lower bound. And for p between 3 to 18 over 5 with initiated LP, I proved with reading who with like r analytical radius of vt over square root of t times absolute value logarithm of t has this lower bound, and even for base of space. And for base of space initiating LP for p between 3 and 6, we can also have this lower bound for the analytical radius. So coming up, a complete solution, the problem, now open question listed by Herbert and Skip State in their 2011 papers is like, what about the complete solution for H gamma for all gamma greater than or equal to 1/2? And roughly speaking, we shall show the analytical radius of this ut over square root of t should greater than or equal to square root 2 gamma minus 1 times absolute value of logarithm of t plus log absolute value of logarithm of t plus kt. And this kt tends to infinity as t tends to plus infinity. So more precisely, joint work with Zhang Li from University of Hong Kong, we can prove this result. For initial data, U0 in H gamma, gamma greater than or equal to 1/2. There exists a time t positive such that this generalized Navier-Stokes equation has a unique solution in this classical space C 0 to t H gamma intersect with L2 from 0 to t H dot gamma plus 1. And furthermore, we can prove there exists T0 less than or equal to capital T, so that for any sufficiently small delta greater than 0, such that this gamma greater than 1/2 plus 2 delta. And then we can prove this for H dot 1/2 plus delta norm of this E lambda T square root of T D at from this UT should be controlled by the right hand side. And here this lambda T equals square root of 2 gamma minus 1 times logarithm of T absolute value plus log absolute value of logarithm of T, and plus 3 beta of T. So here we define this eta j gamma of T equals this maximum for tau between 0 to T. For this frequency greater than or equals to 0.01 of j absolute value of gamma to the power of cosine to the power of gamma times Fourier transform of u in L2 norm. So that's the definition of eta j gamma of T.
With this, we can define this beta t, the minimum of logarithm eta gamma t to the minus 1/2, and this 1/2 times chi gamma minus 1/2 logarithm of t absolute value if this eta j t to the minus 1/2 t is positive. Otherwise, we just take this beta t equals 1/2 times gamma minus 1 log absolute value of logarithm of t. So in particular here, we have this analytical radius of this ut over lambda t times square root of t should be greater than or equal to 1 for any t between 0 to t0. We don't need to take this lower limit and lower limit. So this theorem works for all gamma greater than 1/2. In a paper by Herbert and Skip State, they only works for gamma between 1/2 to 3/2. And we have also a very refined point-wise in time lower bound is like analytical radius over square root t times absolute value logarithm t plus log absolute value of logarithm of t plus kt has the same lower bound like square root 2 gamma minus 1 for all t between 0 to t0. So for any given solution, U belongs to C0 to TH gamma of the general Navier-Stokes system with niche data U0 in H gamma. We can prove rigorously this eta j gamma t tends to 0 as g tends to infinity. And in this situation, the case for eta gamma t to the minus 1/2 t, which corresponds to the Fourier transform of the solution, is included for cosine in the ball with the radius 0.01 to the t to the minus 1/2 for all tau between 0 to t, which yields infinite space analyticity radius of ut. This peculiar scenario does not seem to easily roll out for nonlinear problem. Like in 2D, for radio data, in this situation, the solution for 2D K equation with vorticity. So in this situation, the 2D vorticity equation can be reduced to partial t of omega minus la partial omega, this equals 0. So in this situation, as long as niche data has compact support, the vorticity always has compact support. So in this situation, this eta gamma t to the minus 1/2 t equals 0. So the introduction of this beta t is to accommodate the situation when this data U0 has higher smoothness, say in Hn for n greater than gamma greater than 1/2, whereas the working space is H gamma. Apparently, in this case, U0 in Hn for n greater than gamma greater than 1/2, we have this eta j gamma t should be less than or equal to j to the minus n minus gamma. And then it's easy to calculate this logarithm of eta gamma t to the minus 1/2 t should have a lower bound like 1/2 n minus gamma, the absolute value of logarithm of t minus constancy, which plus the original lower bound of the analytical radius, you gain this 1/2 n minus gamma logarithm of t. And at the minimum, the other cutoff, like 1/2 gamma minus 1/2 logarithm of t, is for convenience of analysis only. In practice, we tacitly assume the working space H gamma saturates the smoothness of U0 such that this eta j gamma t decays suitably slowly as j tends to infinity. So to overcome, for instance, the barrier, like a gamma equals 3/2, we resolved to this high and low splitting. In our situation, for any of this U belongs to Schwarz distribution, we split this A equals low frequency part plus this high frequency part. This N1 equals lambda times capital T to the -1/2. And we define this AL by its Fourier transform equals the Fourier transform of A times the frequency cutoff for the frequency absolute value of cosine less than 0.01 and 1, and for the remaining part for the high frequency. We also define the operator T at on A through its Fourier transformation. This TA Fourier transform equals e to the minus lambda squared of t over 4t plus lambda small t over capital T times the absolute value of cosine multiplied by Fourier transform of this A. The working seminorm x to t is judiciously chosen as this t to the delta over 2 times cosine, absolute value of cosine, to the power of delta plus 1/2. And for the frequency, cosine greater than or equals to 0.10 lambda t to the -1/2 times this Fourier transform of this TA. So here delta is greater than 0 and gamma greater than 1/2 plus 2 delta. So the main idea of the proof is like step 1, local existence of classical solution. The second step, the uniform estimate of this semi-norm of UN in XT. And the last part, we should prove the convergence of T to the delta over 2, T act on UN converges in L infinity from 0 to T0 H dot 1/2 plus delta. So here we should have an exercise caution, since this dot xt is only a semi-norm, which is in fact not norm. The main idea of the proof is like the high frequency part of the solution indeed contribute to the analytic values of the solution. So the crucial part is to prove the following proposition for gamma greater than or equal greater than 1/2 plus delta and the eta 0 being sufficiently enough positive constant. We can prove this cutoff like t, the cosine, absolute value cosine greater than 0.1 n 1 cosine to the power delta plus 1/2, and with this Fourier multiply e lambda t over square root of capital T, absolute value of cosine minus lambda squared of t over 4t act on this Fourier transform of the nonlinear part of this generalized Navier-Stokes equation. This should be controlled by the right-hand side. So the main idea is as follows. For the quadratic term, we have this high frequency cutoff, say 1h act on this Q UV. This should equal like Q U with high, V with high frequency cutoff plus Q UH and V low plus this Q like U low V of H with this one high frequency cutoff, but we don't have low because of this product of two distribution. The support is contained in the summation of the support of the two distribution. So low part with this high frequency cutoff 0.1 and 1, there is no low in this quadratic term. So in this way, we can prove this proposition with this proposition. So the first part, we needed to prove this local well-postedness of generalized Navier-Stokes equation. This is classical. We denote this B equals BU with bilinear part, while partial T of B minus Laplacian B equals QUV, B at T equals 0 equals 0. So we first prove the bilinear estimate for BUV. With this BUV, we can use fixed-point argument to prove the classical well-postedness for 3D generalized Navier-Stokes system. We can also prove similar results in the critical case. For the critical case for U0 in H dot 1/2, we can prove this generalized Navier-Stokes equation has unique solution in the Fujita-Kato space. And here we can also define this zeta j gamma of T, which equals this frequency cutoff for cosine, absolute value of cosine greater than or equal to J, absolute value to the power of gamma, the Fourier transform of U, L to norm. And here we define this lambda T equals like 3 minimum of logarithm of this quantity and the logarithm of T. So here, as before, if this zeta 1/2 T to the minus 1/4 T equals 0, we tacitly define this logarithm as plus infinity. So in this situation, we can also prove this E lambda T times square root of TD at on UT H dot 1/2 plus delta norm should be controlled by the left-hand side. So a refined point-wise inclined lower bound here, we can prove an explicit lower bound like lambda T times square root of T for all T from 0 to T1. And this lambda T depends on this maximum, which is a figure of merit measuring high frequency smallness of the solution. Since we are in critical scenario, we employ T to the minus 1/4 to break the scaling. So in this, as we mentioned before, in this joint work with Zhang and with Gallagher 2003, we can prove the solution, any global solution satisfying as T tends to plus infinity, the analytical radius of solution over square root of T equals plus infinity. Now with our result, I think we can also prove similar improvement for the analytical radius for subcritical initial data in our situation. So that's uniform high frequency smallness in H dot 1/2 space, which I'm going to skip the detail. So now the status quo 2005, the Herbert's steep state conjectures in my joint paper with Dongli in 2004, we have a complete solution for initial data in H gamma for all gamma greater than or equals to 1/2. Roughly speaking, we can prove the analytical radius over square root of T should be greater than or equals to square root of 2 gamma minus 1 times absolute value logarithm of T plus log absolute value of logarithm of T plus KT. And here this KT tends to infinity as T tends to plus infinity. So now the question is like, what about the general LP Sobolev or Besov situation? In order to solve this problem, we need a completely new set of techniques. That's our very recent result. Joint work with Dongli. We almost finished the paper, which should be put on archive in the very soon. Given initial data in this Sobolev space, W gamma P R3 for P between 1 to infinity, and gamma greater than or equals to minus 1 plus 3 over P. Then we can prove there exists a sufficient small time T0 such that for all T between 0 to T0, we have this analytical radius of ut should be greater than or equal to square root of t times square root 2 times gamma plus 1 minus 3 over p times absolute value logarithm of t plus log absolute value of logarithm of t plus kt. And here this kt tends to infinity as t tends to plus 0 plus. So this situation in particular, if we take p equals to this exactly recovers our previous result. So this, in some sense, almost completely resolves Herbert's steep state conjecture without any loss. And I think with this framework in the same paper, we also we work the space with niche data in so-called Bessel space, which decays sufficiently fast in the real space that we work in B, S, P, like compact, which we defined as all this U belongs to B, S, P, infinity. And we also have this limit as this J tends to infinity, this 2 of J of S. Delta J of U equal to norm, this tends to 0, the infinity. So that's a real space we used in our work. So I think this paper we should put in archive in the very soon. So my time is almost over, according to Professor Muha. He told me I have to finish my talk in 15 minutes. So some remark is like, what about 3D anisotropic Navier-Stokes equation? For by 3D anisotropic Navier-Stokes equation, we mean equation of this type, partial t of u plus u dot gradient of u minus Laplacian h of u plus gradient of p equals 0. This is also a topic which I learned from Yang Schumann 20 years ago. For this problem, we can also prove for niche data u0 in some Bessel space like B of S 1/2, which means you have S derivative in x1 and x2 variable, but you have 1/2 derivative in x3 variable. Here, this Laplacian h means partial 1 squared plus partial 2 squared. I proved with my students, if we have a little bit analytically on the third variable for the initial data for u0, say, belongs to some Bessel space B of S 1/2. Then we can prove as long as t greater than 0, the solution is analytic in the horizontal variable, like e to the a square root of t b of h plus delta over 2, because there is no dissipation in x3 variable. In the x3 variable, it's like hyperbolic system. For the initially, the analytic radius is delta. For time positive, it should be delta over 2, b over 3. This solution, u of t, belongs to some Bessel, measured in some Bessel system. So this result is my joint work with my PhD student in New, and this already published this year, last year. And now we are improving this horizontal analytical radius with the techniques we developed recently. So that's for 3D anisotropic Navier-Stokes equation. And even for Prandtl system, we can prove as long as we have some analyticity in one direction, as long as time t is positive, we can also develop result of this type, which is joint work with Weixi Li and Tong Yang. I think we should put the paper on archive in the very soon. And I think, of course, this idea can be generalized to the quasi-geostrophic other SQG questions. And the other direction for this problem, which is largely open, is concerning like the upper bounds for the analytical radius, which is completely open, which I really don't know how to prove. And the last concern is about this problem with boundary. I think our method does not work. I don't know how to do this. I'm going to stop here. Merci beaucoup pour votre attention.
Merci, thank you. Are there questions either in the room or remote questions?
For half the domain, is it for half space?
Yes.
It's working. Yeah. For half space,
I think for half space, for the time being, the techniques does not work. Because we use this frequency cutoff that should be really all for all frequency. We don't know with boundary. We don't know how to do this yet. For the time being, at least, we don't know how to do this.
Yes. Yes, oui, Jeremy.
What about the that you moved about the structure of the nonlinearity?
Structure of the nonlinearity. Just for the nonlinearity, what we need. That's why we work on a generalized Navier-Stokes equation. We just use this. That's why we have a high frequency cutoff here. Act on this quadratic term for these two terms. Because after Fourier transform, the support of two distributions should be contained in the summation of this Fourier transform of these two distributions. So you'll find with this cutoff, you only have this UH, VH, high and high frequency. High and low frequency. Low and high frequency. You don't have this low frequency. Because for low frequency, the summation is on a ball. And this ball disconnect with this cutoff. So that's why you don't have this lower part. And that's the reason why we work for the generalized Navier-Stokes equation. We do not use this exact structure for 3D Navier-Stokes equation.
Bien. Merci beaucoup encore.